So I will kind of go on with my lecture. So my first part focused on kind of general ideas, how to build tweezer arrays, how to control atoms. But and kind of towards the end, I gave you a little bit of the glimpse into the kind of physics of analog simulators. So my second part will actually focus on using the same platform in a different modality. It will focus on using it for digital quantum processing, and also it will be closely connected to this quantum error correction frontier. So let's kind of, in light of my introduction, let's kind of go back. I mentioned to you that there might be different types of encodings which one could explore. And so the qubit basis which we used so far involved basically using the ground state and the Rydberg state to encode the qubit. But this type of approach has some clear limitations. And one of them is that these Rydberg states have a finite lifetime. So and moreover, when we do excite the atoms in Rydberg states, we often actually switch off the traps because the Rydberg atoms are not trapped. So that actually means that you cannot actually, even if you could extend the lifetime of Rydberg atoms, you could not do these simulations kind of indefinitely. So and moreover, this is Rydberg blockade. If you start thinking about it, sort of your Hilbert space, is kind of limited, so you cannot actually do it yourself, James. So, but there are different approaches to encode, and the one which actually is more conventionally sort of suited for conventional kind of quantum computing, like gate-based model, is an approach where you basically use a pair of long-lived states, such as, for example, hyperfine states, so they're basically a combination of electron and nuclear spin states of the atoms, to encode a qubit. And the advantages of doing that is that this state can be very long-lived. It can basically, its lifetime is limited by vacuum, and coherence time can be easily kind of in seconds or tens of seconds kind of range. And so only when you want to do the gate, in this case, you will use Rydberg lasers to excite the atoms in the Rydberg states. And so this actually, like this kind of approach was essentially the thing which, when we started thinking about this kind of Rydberg atoms for quantum computing, this is what we kind of had in mind. And this actually, for a long time, it has been challenging to sort of utilize this approach and kind of implement this kind of approach using high fidelities. And I will tell you a little bit about how this was kind of circumvented. So it was circumvented due to a combination of several things, and one of them was new idea how to do the gates. So this kind of this new idea is by now called sometimes a Levin-Pigler gate, and this idea is basically the following. So if you want to do a quantum gate operation, what you would like to do, you would like to use this kind of Rydberg excitation to basically implement the conditional phase is described here. And the way kind of how to do it is essentially the following. So you would like to kind of utilize this Rydberg blockade in this kind of work in the subspace of these blockaded atoms, and basically kind of excite the atoms in such a way into a Rydberg state so that you actually come back to this kind of desired storage states, but come back with really the right type of phases, and the kind of essentially the idea here is the following. So this state 0, 0, so you excite the state out of 1, 1, the state 0, 0 has no dynamics, right? So this is dynamics is trivial here. So you would like to excite it out of the state 0, 1, so it's a single particle, so it's just single atom excitation in such a way that you come back. But you would like to excite it out of state 1, 1, such that you come back with a conditioned phase. And actually, the difference, so they are both like two-level systems, they can be understood, the dynamics can be understood on the Bloch sphere. But because here we start with 2 atoms in state 1, so effectively the radio frequency to excite a single atom has the square root of 2. So basically, you would like to use now this kind of choreography on these Bloch spheres in such a way that you basically, come back to the same original state, but with a different phase. And this actually can be accomplished, in this pre-living protocol is accomplished by using 2 pulses of light. One, basically has 1 detuning, so basically one evolves around 1, axis on a Bloch sphere. And another one evolves around the other axis, that's from here. And basically, here, because of the square root of 2, this trajectory of Bloch sphere is slightly different. And for the certain detuning, you can basically arrange it such that the phase will be exactly fine. So this kind of is another interesting Bloch exercise, So Bloch sphere is one of the most fundamental things that actually you kind of need to know. And this, is an example where it is really useful. And so I can tell you that, like around 2000, when we first started thinking about this, I spent, many weeks, with some other famous people, very good people. So trying to figure out if one could realize this gate, and we really failed, and actually almost 20 years later, so some aspiring students of postdocs, figured it out and actually really sort of resulted in a full new way of experiments as we will use here. So, so does it make sense? Questions? Yeah. Yes. Well, so that really means is that, you cannot do this. There is a lifetime, right? So you have to do these gates faster than this lifetime.
But in terms of gate fidelity, should I consider this?
It will limit the gate fidelity, in that it does, right? So but one approach is to actually do these gates fast, right? The faster you do it, the better.
In terms of simulation, how long is that atomic time?
What is it?
In terms of simulation, not just doing a game. In terms of
for analog simulation, it will limit the duration of the simulation.
Yeah, what's roughly like the time scale?
So typical time scale for the simulation is maybe some 10 or maybe tens of microseconds. So it's a
thanks.
Yeah.
You comment on why this thinking was hard to find?
Well, so yeah, so kind of one other kind of thing which I should point out is with these two, with the 2 atoms. So the gate which we found in 2001 was if you can excite atoms individually, then this kind of gate fast. It was called, we call it fast gate. So what you could do, you can excite one atom, then just do a pi pulse on the second atom. And then clearly, depending whether it's first excited or not, you will get different results. So one kind of important ingredient here is that in this approach, both atoms are excited at the same time. And this somehow we tried, that we looked, in the past, we looked for a single pulse and we were not able to find it. So These guys are all two pulses. You can do it actually by now with optimal control techniques you can find. I am so sorry. Can we just make a because I'm talking. Just can we make like a 3 minute, maybe you guys can discuss how about we discuss this. Just because I was just give me 1 second.
Just wanted to rebound into the microphone thing because I want to be that we got the credits out you are asking about. So was there any problem here we got or how we so if there's no problem
I think so for people in the front, it's hard to hear what your questions are. So in the back, so if you are talking, it's best to talk in the mic.
Okay, so yeah, please maybe just after you want to ask the question, just hold it a little bit, wait for the microphone, and then speak to the.
All right, so you guys, you just have some good questions. So the break was too short to answer. Okay, all right, so okay, so that's one ingredient, and the second ingredient, which will be very important now in the second. You have all right, okay.
Sorry, so one more question to the gate.
Yeah.
Yes, you have such gauge where you close these loops. I could imagine it's quite sensitive to errors in the pulse length in the Rabi frequency. How robust is it? And did you modify this to make it robust?
It is kind of, in fact, it is can be made quite robust. So what I will, so there is, of course, you have to calibrate it, but one thing is very important. For example, it does not depend on how atoms how closely they sit. So this calibration is basically, is done typically not just for one gate at a time, but it's done now for hundreds of, atom pairs. So the only thing you need to know is just the atoms are within a blockade. So in terms of duration of pulses, and for example, things like light shifts is something that is, of course, is important. But basically, we now have these procedures to calibrate. And actually, to be honest, in the more recent generation, we are not using this living Pichler. I mean, it's a gate which is in the same spirit, but now we use single pulse, and we optimize it using optimal control techniques. Some things like grade, for example. And we developed a procedure which actually we can automatically calibrate it for like hundreds of atom pairs at the same time. But of course, this excitation to become genius and so on. This will all contribute to gate errors. Okay, so the second. Any other questions? Yeah.
Sorry. You got it? Hello. So is it easy to characterize the hyperfine states within a specific atom? Because it seems like we're using this Rydberg manifold in order to create this dipole-dipole interaction. But if there's if this electronic spectra, right, that's complicated, it seems like there'd be a lot of potential for crosstalk, especially if our pulses aren't well calibrated.
Yeah, so these hyperfine states, they are probably the states which are some of the best characterized states in the nature, in part, for example, that the current definition of the second is actually connected to the hyperfine states of the cesium atom. So they actually, it is true that, you can have other transitions, but these are exquisitely controlled. These are as controlled as it gets. Yeah. And they are relatively simple and very well understood.
Great.
Yeah. All right. So this so far is all like kind of, encoding qubits you have to do in any platform, and and doing the gates and so on. So I will introduce now some new feature, which is actually quite special, for the neutral atoms, and that's the idea of reconfigurable architecture. So it turns out that once qubits are stored in a hyperfine states, not only you can store them for a very long time, but you can also use tweezers to move atoms around while keeping the coherence alive. So that's kind of illustrated here on the very simple it's an experimental result. Where, suppose you start with just pairs of atoms, and then in this case, we entangle them in parallel. So it's actually, in this case, we also will create Bell states. And you can sort of verify that these Bell states, are created by looking, for example, at two-atom parity. But then, instead of just measuring, characterizing these Bell states here in situ, what you can do, you can take this atom pair and pull it apart, and separate them by kind of 100 micrometers, and basically again check if this Bell state was preserved. And in fact, what you see is that this Bell state is completely is kind of unaffected by the separation, and so that kind of gives rise to this idea of the reconfigurable architecture, where essentially the idea is the following. Suppose you start by positioning your atoms in some way, and basically in that way the system has some kind of connectivity. So you can then implement this single and two qubit gates, But what you can then do, you can stop the evolution at some point and just move atoms around. Right, and then basically do another layer of data. So basically, in this way, the connectivity of your processor becomes like a living organism. So it's changed, evolved during the computation process itself, and this is very special because typically, for example, the chips which run your cell phones, that actually also they designed and then created optically. But once it's done, you cannot change. The connectivity is defined at the time of design. So here, connectivity can change. And this kind of is a very special feature, which immediately gives rise to kind of several unique opportunities. So one of them is that, the connectivity can be non-local because you first can locally couple some atoms and then to move them around and basically, do another set of gates for the atoms which initially were not near each other. And actually that also enables something which turns out to be very important. And you will see it in a second. This is parallel efficient classical control. So it turns out that, you can execute very complex circuits in this kind of within this model by actually calibrating and optimizing very few parameters. And this actually is, as one kind of scales the system up, it becomes very, very important. So, does it make sense? Okay, so this sort of non-local connectivity opens up a lot of cool new opportunities. So, for example, you can actually combine analog and digital processing. So, for example, you can like an analog circuit, then just freeze the evolution, take the atoms and map them to hyperfine states and then change their connectivity and basically, do some gate operations, then, start the evolution again and so on. So we actually used it a couple of years ago to, for example, measure entanglement entropy, just using the so-called two-copy method, using analog evolution in two copies, freezing it, bringing it together and bring it. So there you can also kind of think about, for analog simulators, if you want to measure, for example, topological entanglement, and you can also utilize this kind of tools. So it turns out that you can use this reconfigurable architecture to actually, kind of create new types of simulators for kind of complicated tasks like chemistry, or maybe kind of like gauge theory. So in fact, Galev will give a talk next week. Maybe he will show a little bit of a preview of some work that we are doing in this area. And, one can also think about, even sort of simulating this kind of, high energy model, like this kind of ideas, CFT. So I think there are a lot of kind of exciting opportunities, and one can basically, do a lot of the simulation in a hardware efficient way. And I would say in many of these things, the ultimate challenge will be to controlling errors, right? So basically, if you have some sort of fidelity, just beyond certain gate depth, your results will not be accurate anymore. And this is a challenge which actually people in the field recognized many years ago, almost 20 years ago. And this was the reason why many famous scientists in the field, they doubted that this quantum computing will ever be real. And that was a motivation at the time. Yeah.
How much does the shuttling speed of your atoms restrict like the types of algorithms and applications that you can?
So this is maybe something we can discuss at the end. So the question here is that this reconfigurable architecture will require some time. So it is indeed the case that in our case, in our system, the gate operations, the kind of which sort of normally define the clock speed can be actually quite fast, can be like a few megahertz, but usually the reconfiguring and also mid-circuit measurement, takes longer. So typical time scale for reconfiguring is maybe 100 microseconds. So it's a kind of a factor of 100 slowed down to what it could be. It's also a factor of 100 slowed down compared to, for example, superconducting qubits. However, what will emerge, hope I will get to that, is that if you really start looking at the kind of complex as executing complex algorithm, so what you really need to think about that in this case is not just the speed of individual components, but you should look at the algorithm as a whole. And so while this reconfiguring introduces some slower time scale, it also enables some very important features which allow you to save in some other ways. And actually, for this reason, this reconfiguring, even if it slows down things a little bit, can be exceptionally powerful. And in fact, allows one to basically almost, it allows some features which basically completely sort of mitigate this time costs.
Okay, and just to clarify, is the problem that you move them too quickly that the atoms will fall out?
Yeah, so the atoms, if you move them, okay, so the time scale for the moving depends on the depth, on your kind of basically trapping frequencies. So, and if it's, if you move too fast, then it just becomes sloshing, and eventually they escape. So you could, doing things faster, this will, like, doing things with higher fidelity and doing things faster is a quest that will never stop, But even at the current level, it turns out that, the savings that this reconfigurable architecture enables almost offset the cost of, and kind of course, it enables to do other things also. Yeah. So the key of my message, the key of my lecture today, if I ever will get to that, is that it is like whenever you think about quantum computers or quantum simulators executing certain tasks, you really need to look at the algorithm as a whole, at the entire thing. Because if you look at certain components, you really can be misguided. Okay. All right. So, okay. So basically, so I will actually leave maybe to the left to talk a little bit about some of the latest advances here. But what I want to focus on now is this error correction frontier. So basically, the way how quantum error correction works is similar in spirit to classical error correction, which is basically you do like repetition. So instead of, just for example, 1 bit of information, you can use 3 bits to encode 0. And of course, it increases, there is redundancy, increases the robustness. You can use, for example, majority vote to determine if the bit flipped. So early on, actually, it was not clear at all whether these ideas can be actually used for quantum error correction for multiple reasons. So first off, in quantum mechanics, there is no cloning theory, so you cannot duplicate quantum information. Also, detecting error here implies making measurement. Usually, if you make a measurement, you destroy quantum information. So the fact that you can actually do error correction, quantum error correction at all, is already an amazing, result. And the way how you do it is you basically, store information not locally. And by doing that, you basically also then introduces ideas of stabilizer measurements. I will illustrate it in a second on an example of a toric code, where you can actually detect local errors without measuring the actual state that you stored. And by being delocalized with logical degree of freedom, corresponding to the so-called logical qubits, become hard to accidentally manipulate. So, but of course, it's clear that this error correction, comes with overhead. So, redundancy, you need many physical qubits to store one logical qubit. Also, it means that, it's actually, hard to manipulate logical degrees of freedom intentionally, since it's kind of accidentally hard, also intentionally, it's very hard. And so, so this is one specific example. It's probably the best known, best studied quantum error correcting code, the so-called surface or toric code invented by Alexei Kitaev. And basically, you can think about it as a kind of a product of 2 classical repetition codes, one which correct bit flip errors and another correct phase flip errors. And the structure of this toric code is basically the following. So you have qubits on this kind of grid, like shown here. And then the stabilizers are the Z and X checks, which are the products of 4 Z operators around a vertex here, or a product of 4 X operators around the plaquette. And so basically you define the kind of computational stabilized subspace as an eigenstate of all of these operators, which by the way commute with each other, and they should all be basically be, +1. These are like these kind of parity checks. And basically in this code, to basically apply X operators, you need to just apply X on all qubits kind of going, for example, from top to bottom, and Z on all qubits going from left to right. And what we see is that these products, they actually overlap only in one space, in one point. So for this reason, they actually anti-commute, So they kind of define this, computation kind of subspace. And if, for example, an error occurs, for example, if one bit flipped here, so then what you do, you basically, look, when you measure the stabilizers, when you do Z checks, what will happen is that this check will show -1 and this will show -1. And so if error occurs at one place, you can very easily basically identify that, oh, here is the bit has flipped, and you can just, go and, either, flip the bit by hand, or sometimes even just record it in a kind of in a software that occurred, just that it visualize this information. So, so of course, the key question is, what if we make the lattice bigger? Does your qubit become more robust or less? So making lattice bigger increases what's called distance of the scope. The distance is a linear dimension of the scope. So it basically corresponds to, how many, basically, for example, bits you need to flip to kind of flip from one logical qubit to another. And as we make a lattice bigger, there are more opportunities for errors, but there are more checks. So what you can see is that, basically depending on how this entire kind of, code constructed and how it works, it can have this threshold behavior. And indeed, what turns out is that this surface code has a threshold behavior. So basically, if your error is smaller than this certain threshold error, which is typically around 1%, then you basically, the logical error probability would be suppressed exponentially with this code distance, right? We'll scale as P of P threshold D +1/2. And so basically, in principle, if you now start with components, which are good enough, by growing this lattice, by increasing the code distance, you can actually suppress the error to, to any level that you sort of desire, and basically execute an algorithm without errors. So I think it's fair to say that it was this theoretical breakthrough of quantum error correction which really caused the field of quantum computing to take off, and many people, including myself, believe that eventually we'll have to switch to doing computation with logical qubits. But of course, you see that there is a kind of a lot of ingredients go. There is a lot of kind of overhead. For example, in terms of number of qubits, in terms of control. So for this reason, up until recently, the experiments, most advanced experiments were limited to very small systems containing, small number like one to two small qubits. So we kind of already this reconfigurable architecture we realized already quite some time ago that it actually can be very useful for implementing quantum error corrected codes. And one example, which is now already is more than 2 years old, we implemented this kind of Kitai's quantum error correcting code. The Tori code is in this case on a torus. You could say, well, it's kind of in 2 dimensions. How can you actually do it? So it turns out that it's actually not too hard. And the idea here is basically the following. So in this case, we have these black dots, which are physical qubits, and the red dots are these qubits which actually measure these stabilizers, do these checks. And basically, to do these checks, remember what we need to do. We need to basically measure this, for example, vertex operators, we need to touch a few nearby qubits, and we can do it by doing the gates. But if we move qubits around, we can not only move things locally, but we also can move things on locally. And this way, we can really wrap this kind of torus around.
Excuse me 1 second. We have a question over here.
Yeah. Sorry.
Can you go back to the previous slide?
Yeah.
So I was wondering, in this lattice, if I want to look at a single logical qubit, will that be entire lattice, or how do I know what is a single logical qubit?
So here, a single patch encodes one logical qubit, right? So, and that's easy to understand, right? Because as I said, this product of x's and product of z's, that's the logical operators, right? So if you want to flip the phase or the bit, you just need to apply the law. But of course, that's the advantage. They're easy to understand and analyze, but it's also a disadvantage because, as people say, the encoding density here is not very high. So you need to use a lot of physical qubits to encode one just logical qubits, and there is now an effort to circumvent it. And this, for example of that is something which is called quantum LUPC codes. So I might mention it towards the end. Let's see. Kind of, I don't know how much I can. Yes.
What do you mean by coils, CNX?
So to flip, for example, if you have an encoded qubit, if you want to flip from 0 to 1, so you need to apply access on all of these, qubits going from top to bottom here, right? So if you apply all of these access, actually it does not change stabilizers, you can change. So it's still in a protected subspace, but you will flip the logical state from 0 to 1. So if you want to flip the phase, you need to apply these going from right to left. And you can see that this product of this and product of x defines is a correct algebra because they only overlapped one spot, only for one qubit, right? And for this guy, TNX anti-commute, right? So that's why the entire operator, this also anti-commute, that's why they define Q. Does it make sense? Yes. It's, like for a single qubit, right? So single GNX anti-commute, right? So all stabilizers commute with each other and commute with these logical operators, but the logical operators anti-commute. Yeah.
So if a 2D code encodes just a single logical qubit, how would I apply, say, a CNOT gate between two logical qubits?
You will, if you're patient, you will see. So actually, interestingly, so if you, for example, now take this thing and put it on a torus, and maybe it's a little bit of a hint. So if you put it on a torus, you can actually encode two logical qubits because you can have basically Z operator going this way and going this way, which clearly commute, and also X operator going this way and going this way. So basically, there are two X and Z's which anti-commute with each other, but commute with each other. It's kind of that in this case, by changing topology, you can encode more information. So, but kind of importantly, so this Tori code we actually can prepare using this two-dimensional architecture by just moving these ancilla qubits around, basically moving them non-locally, such that we can really close the stores, this boundary condition. So the details are not very important here, but what's important is that this entire circuit involving, in this case, I already forgot, maybe 16 physical qubits and 8 ancillas, has been specified by just two voltages. One voltage corresponding to moving atoms up and down, and another one moving left and right. So that's the beauty of this kind of reconfigurable architecture. So this is a sense in which it enables very efficient control. So all of these gates, of course, we do a lot of logic gates. So this red circle is a logic gate. All of them, again, are the gates done simultaneously, calibrated simultaneously, because it's, this is where this digital interaction comes into play. All we need to do is just specify laser parameter, which basically, now are applicable to the entire circuit. Okay, so with that, we kind of come to maybe sort of some of the recent developments. So right now in our lab, we're actually operating a third generation array. So as I already mentioned, the key, one of the key components here is acousto-optic deflectors, which we use to move atoms around. But we now have actually 3 sets of acousto-optic deflectors. Some of them are used to move atoms around. Some of them are used to apply individual rotations on single qubits, and this kind of the system upgrade, we have now larger systems, higher fidelities, and kind of more advanced control. So here are some of the things which actually we had to do to sort of really start exploring this error correction, this logical qubit. So first off, we need high fidelity gates. So I already mentioned that for the surface code, the threshold is around 1%. So ideally, you would like to work way below the threshold. So, and kind of about a year ago, we sort of, improved our gates by using this kind of extending this living Pichler gates with this kind of optimal control ideas, and to actually, push the fidelities to kind of above 99.5%. So we also now using another set of acousto-optic deflectors can address, can do basically, selected single qubit rotation. And again, this parallelism, which is with one pattern, we can, for example, project and do X or Z rotations on many qubits in parallel. And one other thing, which I probably don't have time to really kind of discuss too much, we are also now have an ability to read out qubits in a mid circuit. So what we do, we can use again reconfigurable architecture. We can just plug some qubits from either gate zone or storage zone and move it into readout zone, and just using a focused laser beam, just read out the states individually. So all of this, kind of comes together to sort of this idea of this logical quantum processor, where now instead of physical qubits, we are now starting to think about information encoded in logical qubits, and kind of do gate operations between logical qubits and build circuits from logical qubits. So this actually system slowly starts looking like a real quantum computer. And in fact, it's actually reminiscent to some of the early classical CPU architecture, where you have this different, control unit, entangling zone is like an algorithm unit, and then, storage unit and things like this. Okay, so I don't know how much I can, cover, but at least I want to kind of illustrate the real key idea behind that. And I will do it maybe by answering the question is, how do you do the gates between logical qubits? So this is challenging. And the reason is because your information now is delocalized, between kind of an array of different qubits. So there are different ways to do the gates. Something that you might have heard about. One idea is to do something which is called lattice surgery. Is take these 2 qubits and somehow merge them by kind of combining it with a single big qubit, and then basically separate them. But this is not the approach which we will take, and this is very important. And so I will kind of elaborate on that, So the approach we will take instead will utilize something which is called transversal CNOT gates. And so here we will use this reconfigurable architecture to literally pick up one of these logical qubits and bring it on the top of another, and then do the gates, do CNOT gates, in parallel on all pairs of the qubits. All right, and then afterwards, when it's done, we separate them. So that's the idea. So this actually executes, a 2-qubit entangling gate between the 2 qubits, and has several major advantages. So one, which is perhaps most important, is that it turns out that this CNOT gate is inherently fault tolerant in the sense that errors from one block, for example, if you had an error on 1 qubit, it of course, upon this transversal gate, can propagate to a second block, but it cannot spread. It will propagate to one specific qubit, and actually that's the reason for this fault tolerance, and it has one huge consequence is that the number of rounds of error correction that we need to do will actually not scale with the size of the code. So this is a subtle topic, and I'm happy to answer any questions, but it's actually turns out that, and we realize it more and more, it's actually one big kind of feature. So second, this type of operation enables directly long-range kind of direct connection between logical qubits, and it results in some significant saving for some large algorithms. But most importantly, maybe from the control perspective, you can now think about a logical qubit as a kind of a unit. So this entire batch of atoms, basically will receive the same instructions and can act like a big macro atom, which really encodes quantum information. Okay, so experimental example. So what we'll do here, we will actually implement a logical CNOT with the surface code, which I described. So basically, the approach will be to prepare one surface code in plus state, prepare another surface code in 0, and just do a CNOT. So the smallest case would be 9-qubit code, so it's basically distance free. And what we'll do, we'll measure D stabilizers in one, measure X stabilizers on the other to basically prepare these 2 states and these 2 bases, and then bring them together, and then do the gate, and then separate them and basically verify if the qubits were entangled or not. But of course, what we can do is now we can not only work with D equals 3, we can go to D equals 5, or we can go to D equals 7. And the key property of error correction should be that the operations should improve with the system size with the code distance. So this is very counterintuitive because in each of these cases you create a bigger and bigger entangled state. Usually bigger entangled state will result in more errors, but here the hope is that with the larger state you will actually reduce the errors. And indeed, what we find, for example, if we do the measurements on the largest code in XX and TG basis, we see that they're clearly entangled. And moreover, what we see is that the error indeed decreases as we increase the code distance. Now, that's kind of a high-level result, but there are a lot of interesting subtleties. And one of them is that it turns out that in order to really obtain this result that the error decreases with code distance, what we need to do is we need to analyze these 2 patches simultaneously. In other words, after the operation, we need to decode your state. So we need to do decoding jointly. So this joint decoding is very important. It turns out without it, clearly it does not, work. And the importance of this joint decoding is, it turns out, is kind of very significant in connection with these transversal gates.
We have a question here.
Yeah, can I just finish? Just give me 1 second. And so another thing is basically this, this is important. It's just one operation. So in principle, what we need to do, of course, we need to do it repeatedly and kind of keep measuring this, stabilizers and so on. So so this is not a complete circuit, it's just one element. But Importantly, so basically that, one can see is that this entanglement and quantum operation of logical qubits improve with code distance, and the fact that this correlated decoding is important is actually very significant. We kind of discovered it basically out of necessity because it didn't work out, and actually we now realize it's a very, very important feature. Okay, yeah.
Have you tried to implement some non-transversal logical gates in the system? If you have, and how does the experiments look like?
So to be honest, we have not, and we actually believe that transversal gates is a way to go. And part of that is precisely because first off, the transversal gates are very resource efficient in terms of control, but also because they are fault tolerant, inherently, it's very important. And actually, so maybe the implication of your question is, can you build a universal gate set from transversal gates? And there is a system Neal theorem which actually tells that that you cannot have non-Clifford operations. But actually, it turns out that, for example, the way how to kind of circumvent this is the Neal theorem is to use this, for example, like T-gate, preparing some, states which are sort of non-Clifford and then injecting them. It actually doing that is also a Clifford circuit. We feed forward, so it's a little bit different, but so we can actually use the same techniques which we use here to do that. That's why I think we're not thinking too much about non-transversal gates, but we can, if we have time, I will show you how to use transversal gates, how to do non-Clifford operations also. So, yeah.
Can you extend a little bit on the sort of the subtlety with this correlated versus conventional decoding?
Yes. So, okay. So how much time do I have? 30. I think it's so. How about why don't I wait a little? Let me just I will actually come back to that, and I think hopefully you will see, you will kind of understand. Yes. Yeah. Okay, so let me go on. So let me try to, proceed a little bit. So, okay, so this surface code is just one type of approach. So one can also use different types of codes. For example, color code is another popular code. And so with the color codes, we have done something which is called scheme error correction, where you can actually prepare states fault tolerantly by first creating some entangled state non-fault tolerantly, but using kind of multiple copies to, for example, just use one of these non-fault tolerant blocks to check the preparation of the other block. And actually, this way, it's basically you can conditioning whether this result of this circuit for one qubit is 0, you can actually improve greatly the purity of the other state. So that's an example of the so-called scheme error correction. And that you can, for example, use to sort of have some break even, so you can reduce, for example, spam in the preparation of the this color code below the value which is kind of a physical spam. And actually, what's interesting is in this case, so experiments like this have been done in the past, for example, by continuum group. But so we have done it, not just on a pair of qubits, but we've done multiple pairs. Actually, in fact, the largest system we've done, I think, was 40 qubits in total, like 20 pairs. But so these data are for 4 pairs, and so once we prepared fault tolerantly 4 qubits, of course, we can sort of use them to build a circuit. And for example, we built a GHG state out of this 4 color codes. now kind of, depending on how you analyze this, this final result, you can actually, sort of have different degree of result infidelity. So, for example, if you have non-fault tolerant preparation, you see that this GHG state is barely entangled, so 0.5 is a threshold for entanglement. So if you do fault tolerant preparation, it's actually better. If you do fault tolerant preparation, if you do also some degree of error detection, you basically don't keep all results, but throw away. Some results just keep the results where you have no bugs, no stabilizers violated, so you can have nearly fidelity. And like you can already also see that with this kind of approach, you can, this physical and logical qubits are different. So, for example, usually if you do physical qubit GHG state, what you do, you check off, you look at parity oscillations. Parity oscillations involve changing the phase of GHG state. For logical qubit is very high because logical qubits are digital. So you cannot just change the phase by a fraction. So you basically have to do things like state thermography. Okay, so we've also done some stuff involving logical kind of qubit teleportation, but maybe I will skip this because it's kind of, I think I want to finish and maybe have a little bit of the stuff. So basically, kind of what these examples show is that we now are entering this kind of era of early fault tolerant quantum computing, where we can really start building and testing logical processes in the lab. And in our view, the very important feature which will actually be driving this era will be this idea of co-design. So let me explain what it is. So suppose you have certain tasks. So for example, you want to explore some algorithm. So you have a choice now which error correcting code you want to pick to execute this algorithm. You have also a choice how to compile your circuit, and basically, eventually you have a choice how to implement it. And to really kind of utilize the resources most efficiently, at least in this early fault tolerant era, what's important is to think about this problem holistically. To basically fit for the given algorithm, find the best sort of most optimal error correcting code, which also fits with your native hardware capability. So I will give you just one quick example, and I will try to make sure we have a little bit of time to discuss. So, and it's implementing non-Clifford operations. So there's we already in discussion was mentioned this non-Clifford operations are very important because if you want the Clifford operations, you can simulate, you can just look at operator propagation, basically understand the result of this quantum computation efficiently classically. So you need some Clifford gates. And this is what's called quantum magic. I think maybe Robert will, in his lectures, will talk about the importance of this quantum magic. And this is basically quantum magic is just a kind of a technical term, fancy term for non-Clifford operations. But it is actually challenging to implement this with logical qubits. In fact, in 2D, we can actually not implement non-Clifford operations. So that's why you perhaps need to do this kind of key state installation, injection, and so on. But we asked the question, can you actually, if you don't want to do something very general, if you want to do something specific, can you generate states, logical, encoded states with a large amount of magic? So it turns out the answer is yes. And for that, you need to go to the 3D and so on. And the simplest, non-trivial 3D code is this kind of the so-called 832 code. So in which you have 8 physical qubits, which encode 3 logical qubits. And this kind of the stabilizers and logical operators, you can sort of geometrically think about some edges and facets of this of the cube. And what's most important is that this, because it's now 3D code, you can actually have a transversal non-Clifford operation. And so, the way how you do it is just simply by just rotating, by applying, pi over 8 phase shifts on some subset of the physical qubits, and actually it implements, it turns out to be CCZ gate within this logical block. So this each logical block now encodes 3 qubits, logical qubits, and basically by applying this individual phase rotation, you can actually implement CCZ gate. Okay, so with that, it's kind of like, time driving. So what one could do is now implement actually a quite complex circuit, actually a scrambling circuit, which generates a lot of entanglement and a lot of magic actually. And so the way how you do it, you can start with logical states with all qubits and plus, and then apply interblock CZs and CZs, and then imply some C-nodes with motion between the blocks, and then you can repeat this many times. And actually, in fact, the specific geometry which we implemented involves making, hypercubes out of already, cubes of physical qubits. So, and in fact, it kind of results in this physical connectivity, which is really, quite complex. So that's the kind of, states we implement. So actually, interestingly, in terms of kind of computer science connection, it turns out that this circuit implements the so-called instantaneous quantum polynomial circuit. And it is actually known that this is a circuit which creates a lot of entanglement, it's scrambling, and it's for large number of qubits classically hard to sample from. So, basically, okay, so what we'll do is we'll create a scrambled state and we'll make projective measurement. And for if this system is sufficiently small, like having 12 logical qubits, what we could just do, we can just plot each probability of each bit string. So it's similar, it's a scrambling experiment, similar like Google's scrambling experiment. And so for this 12 circuit, it's easy to simulate it, and actually you can still plot it. So this ideal circuit should give rise to this kind of distribution shown here. This is like a speckle pattern, basically random, strings showing. So the raw result is this. So it's okay. You can see maybe there is some correspondence between the two, but it's not so clear. But now, if you start utilizing this error correction or error detection, in this case, just keeping the samples where stabilizers have not been violated. So what you see, basically the shadow of this zero distribution comes if you kind of have more and more error detection. So basically you see these distributions are really very simple. And you can quantify it, for example, by looking at fidelity, or this, often you can look at logical cross-entropy benchmark. So depending on this error, error detection threshold, how many samples you keep, you can actually have it this, basically approaching one. And what we can now do is also increase the system size, and we went all the way to up to 48 logical qubits. And this is a logical circuit, and we still see that this kind of encoding and error detection still works. It kind of results in logical XCB, which is, actually quite a bit larger than the best possible XCB we could have gotten with our system, and also than what we measured without error detection. And basically, what it really shows you that these circuits really kind of start, these logical qubit circuits start working within the algorithm already. So this is a movie showing how we create this hypercube. And what you will see here is that this is an entangling zone where we, in parallel, do all operations on all of these pairs of atoms. You see there is here. So we make it larger and larger. So here we run out of space, we bring another one. And so we still first entangle locally, and entangle a little bit, more globally, and more globally, and then more globally, and then eventually we basically entangle these atoms all together. So that's how we want to create this kind of entangled state. And actually, okay, maybe I sort of don't want to rush through this, but one could also utilize, once you create a state, you can measure things like entanglement, for example. You create 2 copies of the state, and then using this kind of Bell measurement, this kind of swap trick, you can, for example, measure the logical entanglement entropy. And what is shown here is that, as the subsystem becomes larger, so the entanglement entropy grows, but if you don't use the detection, the error error detection. So your logical entropy keeps growing, but if you start using this error detection, your curve turns into this kind of page curve. The entropy grows up to half of the system size, and if you make a system larger, it becomes more and more pure. So it really shows that you already can start a kind of exploring this for kind of scientific applications for this. This is actually a fast scrambler, so actually maybe Andrew Berry will talk a little bit about it. So it's kind of physics here is somewhat related to the physics of black holes, for example. Okay, so I've kind of maybe want to conclude a little bit, and so there was talk a little bit about lessons learned. And so, for example, one of the things which we already discussed was the fact that this transversal gates, this correlated decoding is very important. So we kind of first started utilizing out of this necessity, but we now realize that it's actually a much more general kind of conclusion. It's actually turns out to be much more important, connected to things like clock speed and stuff like that. Okay, let me try to explain. I will take 5 minutes, less than 5 minutes. So, okay, the idea why correlated decoding is important can be understood as follows. So if you do the logical synod, which actually is, transversally can be done in all CSS codes, in a large class of codes. So if you have, for example, an error on one of the logical qubits, it will propagate to another, but it will propagate locally. So if this physical qubit had an error, this error will propagate to this specific physical qubit and nowhere else. Likewise, if, for example, it was a Z error on one of these qubits, it will propagate, to the upper one also. So what it really means is that if you now, after you did a gate operation and you got some initial density of errors, some of these errors will be copied to the second qubit. So if you start decoding them independently, you have a lot of errors, and you don't know where they originate. However, if you start decoding them jointly, where this basically, where this correlated error can be viewed as a kind of hyper edge in this what's called so-called decoding graph, it's clearly very important information, and you can utilize it to basically figure out where your errors occur and sort of, efficiently correct them. So that's the idea of this correlated decoding. And it's, for example, we used it also in this GAG experiment. For example, physical error occurred here, right? It basically gets copied, many qubits, but this error propagates deterministically, right? So if you, for example, see like, an error in this qubit, and the circuit, you can figure out, it's probably originated from this error. You can just basically account for it, So it actually turns out that you can effectively undo error propagation by tracking where errors occur. So, but of course, these errors, if they occur, if they add in time, that's the entropy. So you need to measure, of course, error correction is still needed. You need to basically reduce kind of the entropy. And actually, it turns out that if you do like a Clifford circuit, by just measuring, periodically, doing these stabilizer measurements, you can precisely decoding the circuit as a whole. You can actually do it kind of very efficiently. So this idea, which we have now demonstrated on 2 qubits, actually can be generalized to the entire algorithm, which involves these Clifford operations. And in fact, what it allows one is to basically reduce the number of these checks of stabilizer measurements, which you need to look around. So in fact, the optimal number is actually less than 1 in this example. But what's actually more kind of interestingly is it turns out that this idea, which in the Clifford case can be sort of understood because in the Clifford case errors propagation can be trapped, can be generalized also to non-Clifford operations. So in operations, for example, where you have some mid-circuit straight out, and that's this kind of new idea which is related to this kind of so-called algorithmic fault tolerance. So maybe the left will talk a little bit about it. So it turns out that in general, for any algorithm involving transversal gates, this type of approach can result in factor of 10 to 100 speed up in terms of clock cycle. So basically, that's what I meant when I said that, for example, if you start moving atoms, you pay upfront cost, but for example, it will allow you to greatly reduce a number of the kind of rounds of error correction. And, that's a real frontier. And so I think that if maybe we'll mention this a little bit. So on the kind of outlook on kind of technical side, these ideas which, I kind of introduced, kind of in the current form, we believe that they should be able to scale directly to systems involving maybe tens of thousands of qubits. And that, for example, like creates a path towards devices with 100 logical qubits, maybe one per million or so error rates. But there are many kind of new opportunities which as a community, our community explores as a whole, for example, using new codes, these quantum LDPC codes I mentioned, using more power efficient prepping, connecting with optical lattices, which actually really, kind of should give rise eventually to the systems which with thousands of logical qubits. But to kind of indicate, that this, I think we're really like undergoing a phase transition into this new era. So this is actually a drawing from, made by students, where they give this kind of logical GHG state. So each line here is not a single physical qubit; it's a single logical qubit. So this really like shows that a change of thinking is taking place. And I think it's an exciting frontier, which in the next few years, I think will be a lot of exciting direction. So I think I used up my time. With that, I would like to thank you for your attention and thank all people who supported that resulted in this. I'm happy to still answer a few questions. Okay. Heads up. Yeah.
Thank you for showing the great progress in terms of the experimental implementation of the full stack quantum error correction. I'm wondering what's the state of art of the mid-circle measurement in the neutral atom platform?
Yeah, so I kind of glanced over that, but as I mentioned somewhere on one of the group, we actually can do it. And the way how we do it is we just plug some atoms from the either entangling zone or storage zone and move them into the readout zone. And then we can basically measure the state without almost unaffected, with qubits in the other zones with error basically being negligible. That's already, we have shown this in our 2020 latest paper that I have presented. So I think there are some interesting technical questions. So for example, now in this paper, the mechanism we used was destructive. So we basically, we like measured the state with very high fidelity, close to 3 nines, but we sort of lost the atom. So such an atom would need to be replaced. So, but that's not necessarily the case. In fact, in the talk next week, if you wait a few more days, you will show how this can be done differently. But I mean, that's one aspect. So the other aspect, which again, I glanced a little bit over this, which is related to this question, is that eventually you need to do this computation for like days or weeks. So right now, these experiments are done in kind of cycled way, where you first, create some atom array. I mean, you reconfigure, you do all sorts of things, right? And then, the experiment lasts for maybe, a second or something, and then you sort of have to start from scratch. This is not how the computation will be done in the long term. In the long term, you will basically be doing computation and you will have a fresh atoms being kind of shuttled to the zone. Again, a lot of progress is being made. But and I think that we will see, results of that in the next probably few months, so. But it's mostly, this stuff is mostly technical,
Got a question over here. Thanks.
I have a question. So maybe in this algorithm where you entangle the 4 logical qubits, you showed that with error detection, you can basically
That's
almost approach one fidelity of one. So I wonder if you lose an atom, for instance, during the gate when it's in Rydberg state, does this account for, let's say, spam error? Because you get basically a dark event, or is it a much more harmful error which is not covered?
Yeah,
captured by the color?
yes, yeah. So this is a very good question, and it's a little bit related to my to what I just said. So indeed, during the computation, there is a small probability, and right now we believe that it's a probability of about 10 to the minus 3 that the atom during the Rydberg gate operation is actually lost. So these can be damaging, right? Because of course, if this atom is lost, then this error will also propagate, and you have to really, account for that and track it. So it turns out that if you know that the atom is lost, you can, sort of convert this error into a so-called erasure error. And these erasure errors are actually much more favorable, correct? Because basically, if you're and it's easy to understand if you have, for example, in a classical repetition code, if you have, initially 3 zeros, if one of them turned into 1, right, you can correct it. If 2 of them turned into 1, you cannot correct. But if, for example, 1 atom was lost, or 2 atoms was lost, you still have the 3rd atom. So it's kind of, there is a, so, and actually, we believe, and it is very clear that, handling these errors correctly, handling this loss is very important. So you, for example, need to think about, specialized decoders, which make use of that. And moreover, it's also very clear that, if you do a computation, you need to sort of refresh. You cannot just, so for example, you cannot just keep your data atoms being in one, kind of spot for a long time. But many of the codes, in any case, involve periodically swapping from data from ancilla. So actually, okay, the short version is, it's very important, but it's actually more like an opportunity. It's more of a challenge and an opportunity, because some of these errors can be corrected very efficiently, and that's actually something that the community is working. Yeah. But you will have to, of course, replace you. That's why also you need this fresh, atoms should come. Yeah.
So I know some of these thresholds depend on specific noise model of the hardware.
Yes, absolutely.
So do we have any sort of knowledge about what sort of noise model these hardwares have?
Yes.
Different types of hardwares have, or?
Yes, absolutely. So this, and of course, these are we have some noise models, we have good understanding of errors.
Mm-hmm.
But of course, even for any given sort of setting, depending on the circuit, the noise model changes slightly, right? And for example, to optimize decoder, you really need to know that.
Yeah.
So, and I mean, that, but there are ways to characterize it, quite efficiently. In fact, some of this kind of new developments is because you can do things in parallel. This calibration and characterization can be very fast, but in particular, this simple noise model where you just have kind of whatever Z and X and so on. I mean, they are sort of incomplete. For example, like atom loss or leakage, is what, it all can take place here. And, kind of understanding that really is super helpful to actually improve decoders, improve the codes, bring thresholds up. And this is, that's part of the code design, basically, right? And this is super exciting frontier. Actually, there's a lot of progress being made. Maybe Dalia will talk a little bit about this.
Cool, thanks. Yes, so one more question.
Could you comment on what will be the major challenges for implementing good LDPC using practical architectures?
Yes. So yes, this LDPC was I mean, I have some slides extra, but maybe I will. So, okay, so maybe let me explain what is LDPC. So this, like surface code. It's an example. It's the code which is extremely well understood. So it's an example of the broader family of something which is called low density parity check code. So, and for the surface code, particular, when you measure these stabilizers, the stabilizers operate, involve local operators. So, and there are many consequences of that. One of the consequences, it turns out that the encoding density is actually very small. So for the surface code, basically you need kind of if a distance kind of the code is d, so it means that you need d squared of the physical qubits to encode one logical qubit. But actually, it turns out that if you relax this locality constraint, if your stabilizer measurement can involve product of operators, which still no weight, that's low density, low density, but can be non-local, then you can actually create a family of the codes, which is so-called, quantum LDPC codes, in which the encoding density can be much higher. So that's the idea. And of course, with this reconfigurable architecture, this non-local operations are very easy. So, and in this case, what you can do, you can take a code block, and you can basically encode many logical qubits, kind of in the same permutation of physical qubits. So that means that you can have, for example, encoding density much higher. That's an opportunity. The challenge is the following. So to create these LDPC states, there's very efficient ways. It's actually described in some of our papers. But the challenge becomes how to do gate operations. In particular, how to do gate operations in parallel. Because now you have like this entire, block encoding many qubits. So what you can do, you can, for example, teleport qubits one at a time into maybe some other buffer zone. But then this one at a time is not bad. It's basically you lose parallelity, right? So basically, to really make them useful, this quantum LDPC codes, you need to not only increase the coding density, but you have to preserve this parallelism, because otherwise the cost that you win in terms of space, you pay in time. And so there are actually a couple of new papers, which actually I have not kind of, I should add them. So both from our group, also from IBM group, which shows how to start maybe circumventing this parallelism threshold. So they allow one to actually do gates in parallel, and it involves in this kind of, in our case, the idea is to use this Pauli, so-called Pauli product measurements, but actually much more work remains to be done. So the key is how to use this LDPC code to do computation. That's a key challenge, But I mean, there are many opportunities also, because, for example, like in many cases, the gates that you need to do is a kind of parallel gates, sort of, which involve identical operations. So in this case, for example, maybe these LDPC codes, parallelism can be restored. But I mean, that's again example of this code design. Depending on the problem, you have to really think about, in this case, this high density code, really to implement things both efficiently in terms of space, but also in terms of time. And now, of course, it has to be done with this algorithmic fault tolerance, which reduces the number of of rounds of error correction. It's additional required, but this is a super exciting frontier, which many of you guys hopefully will contribute. Yeah.
Wait, I saw it first. Yeah.
Thank you very much for the talk. I just had a question regarding post-selection. You mentioned that being used in a couple of the experiments. I was wondering what specifically you're post-selecting it. Is it like a circuit operation or something mid-circuit? And if in the long term post-selection, you think it would still form part of like future algorithms, or is something we need to eventually work around as well, because it introduces any overheads that we might not like, or it's negligible?
So in this, in particular, like in this, for example, 832 code, what we do, we post-select on correct values of stabilizers. And of course, it improves fidelity and so on, but of course, it happens at the expense of throwing up some data. And kind of in the long term, okay, in this case, it improves our signal to noise ratio, so it's strictly useful. In the long term, of course, this cannot be the only solution, right? Because it basically reduces the number of your data. Your data becomes good, but the amount of data, decrease exponentially. So in the long term, you absolutely will need to have this mid-circuit error correction, where you basically just pump the entropy from your system. Of course, to some extent, you will always, at least in a foreseeable future, you will use some degree of post-selection, but this cannot be the only solution. So what our experiments, which I showed here, they demonstrate that we can improve the algorithm using our logical qubits, error correction and so on, but they don't show that we can improve the circuit depth. And so to improve the circuit depth, you really need to make multiple rounds of syndrome measurements during the algorithms to pump the entropy out, right? Because you create entropy.
So you showed how to implement the boundary conditions for the torus and for the hypercube. And my question is, are there any known limitations to implementing the different topological spaces, or you can like embed anything within the lattice with shuttling?
Yeah, so in principle, you can embed anything. I mean, the real question is how hardware efficient.
So this only is limited by the certain compilation, basically.
And it's limited by circuit combination. It's also limited by parallelism, right? So we ideally would like to kind of move a big fraction of the atoms at a time, right? So with one step, that way we accomplish a lot of operations. And so there is a kind of interplay, there is optimization. For example, for this QLDPC code, there will be some kind of trade-off. Some of the codes you can implement super efficiently. Maybe they are not the best QLDPC codes, right? So like the codes which naturally, for example, in this example, the hypergraph codes are the easiest to implement because it means that you can sort of move columns and rows. But this is actually, again, like that shows that in this kind of co-design circle, this compilation is like also super important, right? And result in savings which are orders of magnitude, right?